Good morning, everybody. Any questions on the material so far? Okay. We assigned homework 2, so we'll have a week, and if we need time, we'll push it.
Okay.
Does that make sense?
Have we already covered the material?
The material is on the sampling theorem with homework 2, so we're still covering it. Okay, so in the previous class, we looked at the sampling theorem, and we looked at the math, and we got the expression for expressing the sample signal. And we said the sample signal, the Fourier transform of the sample signal, is equal to 1 over t, the summation of the x of w minus kws. What does this mean? It means we're going to have replicates of xc, the Fourier transform of the original signal, repeated every omega s, and it's going to be scaled by 1 over t.
Good.
Okay, so what we're going to be doing today, we're going to be continuing with that.
You got sound on?
We're going to be continuing with that.
Yep, sound.
That was a sound comment. Okay, so we're going to look at continuing the sampling derivation, and then we're going to look at the reconstruction of the signal. And here, continuing with sampling and sampling theorem. Okay, so what we're going to look at first is how does the Fourier transform of the sample signal relate to the discrete time Fourier transform? So how does the Fourier transform of xs of t relate to the discrete time Fourier transform of x of n? And then we'll do an example and we'll illustrate all this. So we calculated the Fourier transform of xs of t, but we want to see how does the discrete time Fourier transform relates to it. So starting with xs of j omega, this is the Fourier transform of xs of t, which is equal to the integration from negative infinity to infinity, the summation from n equal negative infinity to infinity, x continuous of nt, delta of t minus n multiplied by t, e to negative j omega t dt. So this is the signal xs of t, and this is the expression for the Fourier transform, the integration e to negative j omega t dt. Now what we can do, we can take this summation outside of the integration. So we can write this as the summation from n equal negative infinity to infinity, x continuous of nt, and then multiplied by the integration from negative infinity to infinity, delta of t minus nt e to negative j omega t dt. The integration of a summation is the summation of the integration, and xc of nt is just a constant that we can take out of the integration. Now what is this equal to? What is the integration of delta of t minus nt multiplied by e to negative j omega t dt equal to? Anybody remembers? Without looking it up? Shifting theorem, shifting property. I have a function, I'm multiplying it by a delta that is at nt. What is the integration going to equal to? That function at nt. So this is going to equal to the summation from n equal negative infinity to infinity x continuous of nt multiplied by e to negative j omega multiplied by n multiplied by t.
What's big T here
N
again?
is the time index, the index. T is the sampling time. So this is continuation from what we've done in the previous class. So we took the continuous time signal, we multiplied it by the impulse train. So every t seconds we're taking a sample. Okay, now we can write this also as the following: the summation from n equal negative infinity to infinity x continuous at nt is nothing other than x of n. And if I were to substitute for omega multiplied by t, I can write this as e to negative j omega multiplied by n. Together? Is it clear what we've done? And is it clear what the difference between xc of nt and x of n?
One's continuous, one sample.
Yes, one of them, this is discrete signal. These are the samples taking when the continuous signal at nt. This is a continuous signal, xc of nt, the samples from the continuous signal. X of n, it is understood when I say x of 5, it means x continuous at 5 multiplied by t. And here we use the square brackets versus these brackets. Okay. Now if I look at this expression that we came up with, what is this equal to? What is this expression of?
Fourier, right?
The discrete time Fourier transform. So this expression is equal to x of e to j omega. So therefore, to conclude all this, x of e to j omega, which is the discrete time Fourier transform of x of n, is equal to xs of j omega. All what I have to do is to replace w with omega over t. This is the Fourier transform of xs of t. And this is going to equal to 1 over t, the summation from k equal negative infinity to infinity, x continuous of j of omega minus k multiplied by omega s, when omega is equal to omega over t. Does that make sense? So all what we're saying is the discrete time Fourier transform of the discrete time signal that we generated from sampling is going to have the same spectrum as the Fourier transform of the sample signal. The only thing I have to do, I have to replace omega with w multiplied by t. Okay. Let's look at an example and illustrate all this. So let's say, as an example, given
Is that an E to the J? Sorry.
yes, e to, where is it?
An XC, is that E to the J or that's?
All the way over to the right.
Here?
Yeah.
xc, parentheses, omega minus k omega s.
Okay, so there's no exponent there.
No, there's no exponential. So given the spectrum of a signal, x of j omega below, we're going to plot xs of j omega and x of e to j omega. The signal has a maximum frequency that is equal to 2000 hertz and is sampled every t equal to 0.125 millisecond. If t is equal to 0.125 millisecond, then we can calculate omega s equal to 2 pi divided by t, which is equal to 2 pi divided by 0.125 times 10 to negative 3, which is going to equal to 2 pi multiplied by 8,000 radian per second. Second. Okay. So we're going to sketch the spectrum of xs of w, and we're going to plot the spectrum of x of e to j omega. So let's do that. So this is the signal. And let's put them all in one graph. Okay. Okay, so my original signal has a spectrum that looks like this. And this is 2 pi multiplied by 2000. And this is omega. It has a magnitude of 1 when omega is equal to 0. This is 2 pi multiplied by 2000. Now, if the signal is real, I mean, you know, the spectrum is going to be symmetrical. Omega, the positive frequency is negative frequency. There is a symmetry around the y-axis. Okay, so this is my signal, xc of j omega. This is the continuous time signal. I sampled this signal. I took a sample every 0.125 millisecond. I want to see how the spectrum looks like and how does the discrete time Fourier transform looks like. So starting with xs of w. What is xs of w going to look like? What is the spectrum of the sample signal? How do we know it? Xs of w is going to equal 1 over t, the summation of x continuous of w minus kws. Together? And this is what we've done in the previous class. The last thing we derived is that xs of w is going to equal 1 over t, x of w minus kws. So therefore, if I come here, how is the spectrum going to look like? It's going to have the spectrum repeating every ws. This is omega s. This is to omega s, and this is going to continue from negative infinity to infinity. This is negative omega s, and so on. Together? Is that clear, everybody? So this signal, this spectrum corresponds to a continuous time signal. So let's say this signal looks something like this in the time domain. I came here, I sampled this signal, so I have now impulses that looks like this. This is time domain. The spectrum of this signal that is sampled of this signal is going to look something like this. What else I need to add to here? This is gonna, the magnitude is gonna equal to 1 over t, which is gonna equal to 8,000. Is that clear? What is t equal to? 0.125 millisecond. 1 over t is going to equal to 8,000. Where did this 1 over t come from? Why did we have to scale it by 1 over t? From the expression that we derived. The expression says 1 over t, the summation of xc of omega minus omega s. Make sense? So this is 1 over t. Okay. So this is the Fourier transform of the sample signal. How does the discrete time Fourier transform look like? It's going to look exactly like the Fourier transform. The only difference is the axis is going to be scaled by, what is it going to be scaled by? By omega equal to w multiplied by t. So therefore, at this frequency, this is going to equal to a 0, and I have to label this. This is 2 pi multiplied by 2,000. What is this omega s equal to? 2 pi multiplied by 8,000. We calculated it. And 2 omega s is going to be 2 pi multiplied by 16,000, and so on. Now here, this axis is w. The new axis for the discrete time Fourier transform is omega. And this omega is equal to w multiplied by t. So I'm going to take each one of these labels here, and I'm going to multiply it by t. So what is this point going to equal to? 2 pi. Originally it was multiplied by 2,000, but now I have to multiply by t. And what is t equal to? 0.125 millisecond, or 1 over 8,000. So this is going to be over 8,000. Is that clear? Anybody following? All what we're doing, we're taking this axis. It used to be w. We're going to change the label to omega. Omega is equal to w multiplied by t. So each one of these frequencies has to be multiplied by t, which is equal to 1 over 8,000. Again, t is equal to 1 over 8,000. Okay. So at this frequency, what is this going to equal to? It used to be 2 pi multiplied by 8,000. I'm going to multiply it by t, which is 8,000. And therefore, it's going to be a 2 pi. And then we're going to have another repetition, and so on and so forth. So this is going to equal to a pi over 2. This is going to equal to a 2 pi, and so on. Is that clear, everybody? Okay. This is pi over 2. So if you look at the discrete time Fourier transform, we notice that the discrete time Fourier transform repeats every 2 pi. It's going to repeat every 2 pi from negative infinity to infinity. And if you look at this discrete time Fourier transform, also we're going to notice that between negative pi and pi, somewhere here, it has all the information about the signal that we sample. Between negative pi and a pi, we have the spectrum of the signal that we sample. And also, the discrete time Fourier transform is very similar to that of the Fourier transform of the sampled signal. So let's write these down, and then so the discrete time Fourier transform repeats every 2 pi, and in the range when omega is between negative pi and pi, this frequency range contains all information about the signal. Okay. Now the question that we're going to ask is, under what condition does the discrete time Fourier transform of x of n has the frequency characteristics of the x of j omega, the Fourier transform of x continuous of time? So the question, under what conditions does x of e to j omega, which is equal to discrete time Fourier transform of x of n, under what condition does has same frequency characteristics as x continuous of j omega, which is equal to the Fourier transform of x continuous of t. Okay. So we're going to assume, to answer this, we're going to assume that we have a signal is band limited to a frequency range that is less omega m. So we have a signal, the original signal that we're sampling is limited to omega m. So if we have a signal that is limited to omega m, we're going to look at two cases. The first case, and let's plot a line here, we're going to look at is when omega s is greater than twice of omega m. So the first case is omega s greater than twice omega m, and the second case when omega s is less than twice omega m. How does the Fourier transform look like of the sample signal when omega s is greater than twice omega m? It's going to look similar to the one we just did. So I'm going to have xs of j omega is going to look something like this. This is a over t, and then I'm going to have a repetition this is omega s, this is 2 omega s, and so on and so forth. This is omega m. What does omega s greater than twice omega m mean? If I look at this frequency here, what is this frequency equal to? Anybody? Excellent. This frequency is omega s minus omega m. Agree? This distance is omega m. If this is omega s, what is this going to be? Omega s minus omega m. Together? Okay, so if omega s is greater than twice omega m, what does that mean? It means that omega s, if I look here, if omega s is greater than twice omega m, what does that mean? It means this point here and this point here are separated. You see that? If omega s minus omega m is greater than omega m, it means omega s is greater than twice omega m. So when omega s is greater than twice omega m, it means there's a gap here between this end and this end. So if I look at the spectrum, apparently the shape is preserved. Now let's see what happens if omega s is less than twice omega m. So I have my original spectrum here. This is omega m. And if omega s is less than twice omega m, what does that mean? That's the same as saying this is going to be before this point here. So this distance here is going to be in negative. So in this case, I'm going to have a replications, but these replicas are going to be overlapping. So this is still omega s, this is omega m, and this is the case when omega s minus omega m, omega s minus omega m is less than omega m. Omega s minus omega m, this point is less than omega m. This point here, which is omega s minus omega m, is less than omega m. Okay. So in this case, there is an overlap between the spectrum, and there is no way to obtain the original spectrum, this original, from this spectrum. Although we are plotting this like this, in reality, how is this going to look like? These are going to be added together, aren't they? So how does the spectrum going to look like? It's going to add up together. It's going to look something like this. So we're going to have a spectrum here till here. It's going to look something like this. Does that make sense? These gonna add together to give me this red spectrum that here. Now once I have this red spectrum, there is no way for me to take this red spectrum and get back the original spectrum of the signal. What do we call this? What just happened? What else?
Aliasing?
Yes, it is called aliasing. What is the aliasing? These frequencies from the neighboring repetition is overlapping with the original frequency of the signal. Make sense? So the frequency, these components of this replica are added to the frequency of the original signal in a way that we cannot separate them. So in this case, there is an overlap between spectra and there is no way to obtain x continuous of j omega back again. And the phenomena where high frequency interfere with the lower frequencies due to sampling is called the aliasing. Is aliasing desirable or undesirable?
Undesirable.
Undesirable.
I guess sometimes it could be desirable if you wanted to sound a certain way, right?
Yes. Usually it is undesirable, unless by design. Okay. So this brings us to Nyquist theorem. So what does the Nyquist theorem says? Looking at these graphs.
At least double the WN.
Yes, more specifically. If I have a signal that is band limited to Wm, then I can sample that signal at a rate that is twice that Wm and be able to recover the original signal. How do I recover the original signal? This is the sample signal. How do I recover the original signal? If I want to recover the original signal, filter. I can just take filter that will only allow this spectra to go through. I will get back my original signal. Does that make sense, everybody? So that brings us to the Nyquist theorem. That says if we have a signal xc of t is a band limited signal with xc of j omega equal to 0 for w greater than w max, then xc of t can be reconstructed from samples only if the sampling frequency omega s is greater than twice multiplied by omega max. Or equivalently, t has to be less than pi over w max. Okay. So a few things to note here about the sampling theorem. What the sampling theorem says, if you have a signal that is band limited, so it is important, if I want to sample a signal, what does the signal have to be? Band limited. What does band limited mean? There is a frequency, omega, beyond which there is no component to the signal. Does that make sense? So, such that xc of omega equal to 0 when omega is greater than w max. So there is a maximum frequency beyond which there is no component, no spectra of the signal. Then we can always reconstruct the signal if I were to take samples that are taking at a rate that is omega s greater than twice the maximum frequency of the signal. Okay.
What is that? I thought it was Shannon's theorem.
It is the same. Yeah,
They
Shannon,
work together, right?
Nyquist, yeah, all have different different statements that are the same result of having the Nyquist theorem. Different ways of arriving at the same formula for the Nyquist theorem. Okay. So now that we sampled the signal, how do we reconstruct this signal? So we're going to look at the reconstruction of continuous time signals. So we're going to assume we have a signal that has been sampled and such that the Nyquist theorem is obeyed. So we have a signal that, assume that a signal has been sampled at sampling frequency greater omega s greater than twice omega max. Then the original signal can be recovered from these samples by using the signal reconstruction. Okay, so given that we have the samples of the signal, how do I recover back XR of t? Now these are the samples that we obtained. So what does that mean? This could be, for instance, an audio file that has the sample values. So this file have the samples 50, 91, 13, 16, etc. How do I take these samples that I have that are x of n and generate back my audio signal xr of t? Go ahead. Inverse. Okay, so this is the process, and see if you agree. We're going to go through 2 steps. The first step, we're going to take these samples and we're going to convert them to an impulse train. So this will give me xs of x continuous of t. Together? What does this do? I'm going to take these 50, 91, the samples, and I'm going to generate a signal. This signal here looks something like this. This is 50. This is 91. This is 13, this is 16, and so on and so forth. And this is 0t, 2t, 3t, and this is my xs of t. Make sense, everybody? So starting with x of n, the discrete time signal, I'm going to take these values, I'm going to generate impulses at every t seconds. The magnitude of the impulse is going to be proportional to these values. What do I have to do next? I'm going to take it through an ideal low-pass filter, h of j omega. It has a bandwidth that is equal to omega cutoff. And that will give me the recovered signal, x recovered, xr of t. Now going back to the graph that we've done before in the previous class, in the previous slide, what is that equivalent to? I've taken the samples that are in the file. I generated xs of t. The spectrum of that is going to look something like this. Together? Then I'm going to take it through a low-pass filter. The low-pass filter is only going to allow this to pass through. Then I got back my original signal. So that's what the 2 blocks say that we added here. Is that clear, everybody? Okay. So therefore, if we are obeying the sampling theorem, if omega s is greater than 2w max, then xs of j omega is going to look like something like this. And again, we're going to keep using this triangular shape just because it's simpler to plot. This is going. We have Wm, and here we have omega s. This is omega s minus omega m. And this is A over T. This is negative omega m. This is negative omega s plus omega m, and so on. So this is xs of j omega, which is the spectrum of this signal here. So here, this is how the spectrum is going to look like. Then we're going to pass this through an ideal low-pass filter. How does the ideal low-pass filter look like? It's going to look something like this. This is W, this is T, this is H of j omega.
So it's confusing to me because that looks like a band pass filter,
No.
but it's because it goes negative, and that's why we consider it a, because it's a window, right?
Well, any filter is a window. Okay, so the filters, so on the side here, I can have a low-pass filter. It's going to look like this. I can have a band-pass filter. It's going to look like this. I can have a high-pass filter. It's going to look like
Oh,
this.
it's because of the symmetry of the, okay.
It's a low-pass filter because it has, why is it low-pass filter? What is the low frequencies here? This is zero frequency. This is the lowest frequency. So this allows the low frequency to go through. Make sense? Low-pass filter, band-pass filter, high-pass filter.
Why does it make sense to plot the negative omega here?
Versus, what do you want?
It just doesn't mean anything to me, I guess. It's like, how do you have a negative frequency?
It's a good question. So if the signal is real, then the spectrum of the signal is always symmetrical about the frequency, about omega. Now one way, a simple way to see this is that if I have a cosine omega t, what is this equal to? E to j omega t plus e to negative j omega t over 2. So at any frequency, this is made of a positive frequency and negative frequency. Together, they give me this real signal. Does that make sense? The same thing with the sine, with any sinusoidal signal. You can think of it as made up of two frequencies, a positive frequency and negative frequencies. Okay. Now looking at this, this is a t. I can write this as a t multiplied by the rect of w over 2 omega c. T rect omega over 2 omega c, which is the width of this filter. Now, what is the condition on omega c for me to be able to recover my signal? What does omega c have to be? What is the range of omega c? Looking at here, what does omega c have to be? What is the range of omega c? Has to be between omega m and omega s minus omega m, isn't it? Any value between this range will give me back my original signal. So omega c has to be greater than omega max and less than omega s minus omega max. Now usually omega c is going to equal to omega s divided by 2. Okay. I mean, let me just point out one thing before we move on. Now you see, we are, because these are separated, there is some freedom in choosing this filter, isn't it? I can choose it. Omega C can be anywhere between omega m and omega s minus omega m. There is some freedom in choosing the filter. And the farther this replica is, then the more freedom I have of this filter. You see it? If this is farther up, like much farther, then I can have any filter that has a cutoff from here all the way to whatever this starts will give me back my original signal. Make sense? But what is the I mean, that is a good thing, because then any filter will give me back my original signal. What is the expense of that? What is the cost of that?
You can't go back and adjust adjust your sampling frequency.
Well, it is related to sampling frequency. Like, what is the expense I have to pay in order to make this farther from this?
Sample more.
I have to sample more. Omega S has to be larger, which means I'm taking more samples. So you see it? If I take more samples, this is going to be moved away from this. That's something I like, because then I have lots of freedom in choosing my low-pass filter. But the expense I'm paying is I'm taking more samples. Together? Okay. I want to emphasize one thing. I mean, by the time we've done this sampling, I want everybody to be able to visualize what happens exactly to the signal in the time domain and the frequency domain. Together? In the time domain, in the frequency domain. It should be like so clear that you can look at it and you can see it without having to generate it in MATLAB or in the lab. Okay. Now, lots of these are straightforward, but they're going to add up together that eventually you're going to have to really think about it and look at it and make sure like it is, you're convinced everything is adding together. Okay, so if we have this cutoff frequency, then if I pass my sample signal, I'm going to get back my original signal, which is omega m. This is going to be the spectrum of X recovered of j omega. This is going to be A, and this is W, and this is my original signal. So since X recovered of j omega equal to X of j omega, then XR of t is going to equal to X of t. Therefore, we reconstructed X of t. Now we're going to see, we call this ideal filter. We're going to see why this is ideal filter, and then we're going to see what's practical and how to do it in real life. Okay. So this is the filter that we're going to have to pass these samples to in order to recover my original signal. Agree? Everybody? We're together on this? Now, what does this filter look like? What is this low-pass filter? Since you guys done the homework, you should have got an idea. What is this low-pass filter? How did it look like in the time domain? Yes? Those who looked at their graphs. How does this look like in the time domain? This filter has a spectrum that looks like this.
Yeah.
What does this look in the time domain? Anyone want to guess? What is it? Sink. Excellent. This looks like a sink. What does that mean? Let's see. So in the time domain, what is it? Yes, in the time domain, it's going to go from negative infinity to infinity. In the time domain, the process that we showed with these two blocks is going to look something like this. I have the sample signal, xs of t, is going to equal the summation from n equal negative infinity to infinity, x continuous of n multiplied by t, delta of t minus n multiplied by t. Agree? This is the sample signal that we generated. We took impulse train, we scaled each impulse by the samples that we're having. And then h of t is going to look like this. Sine omega cutoff t divided by pi multiplied by t. Where did I get this from? From the inverse Fourier transform of the rect. With me, everybody? If I go to Fourier transform tables, Fourier transform tables tell me if you have a signal in the frequency that looks like a rect, in the time domain, it's coming from a sink. And this is the expression for it. H of t is going to equal t sine omega ct divided by pi over t. Sine of t over t is a sink. Okay. Now then, how does this process work? So here, going back here, this filter in the frequency domain, it looks like a, in the time domain, if I were to look at everything in the time domain, how does this look like? A sink. So, what is the output of this filter? How do I find the output of this filter, the low-pass filter? How do I find the output if I know the input? What is it? How do I calculate the output of a filter? Convolution. Excellent. I have a filter. I can do it in the frequency domain. In the frequency domain, it's multiplication, straightforward. I multiply this, zeros and one, or non-zero. It is going to eliminate everything. Straightforward. I can visualize it, straightforward. In the time domain, I can do it too using the convolution. What is the convolution tells me? XR of t is going to equal the sample signal, XS of t, convolved with h of t. Agree? What is h of t? H of t is this block here. This is h of t in the time domain. Okay, pay attention with me. Now what is this equal to? This is going to equal the summation from n equal negative infinity to infinity, xc of n multiplied by t, delta of t minus n multiplied by t, convolved with h of t. Together? Everybody? Okay. What is this going to equal to? Anybody want to try to give me what this expression is equal to? What is a delta function convolved with h of t going to give me? What is a delta of t convolved with h of t going to give me?
H of t.
Why?
It's an impulse.
Because by definition, h of t is the output of the system when I apply the delta. When I apply delta, is the same as saying the delta convolved with h of t as the output. It is h of t. Correct?
Yeah.
Everybody agrees. Delta convolved with h of t is h of t. Okay, if I came to this delta and I applied it tomorrow, what should I get? H of t tomorrow, isn't it? So if I shift the input, the output is going to shift. So therefore, what is the convolution going to equal to? T minus nt. Together? Again, if I applied an impulse at 0 to the h of t, I'm going to get h of t. If I apply it tomorrow at 10, I'm going to get h of t shifted to 10. And this is what this formula says. If you shift, every time you shift nt, you're going to get h of t shifted by nt. Agree? Why? Because h of t is time invariant. If I shift the input, the output is going to shift. Okay. Now what I'm going to do, I'm going to just substitute for the value of h of t. What is this going to equal to? N from negative infinity to infinity, x continuous of nt multiplied by h of t minus nt is going to equal t multiplied by sine omega c multiplied by t minus n multiplied by t divided by pi multiplied by t minus n multiplied by t. Agree? This came directly from this. This is h of t. I need h of t minus nt. So I just substituted for it. And I should have omega cutoff, not omega c. Together? So these are the samples. And this is my interpolation function, because this is ideal. Now in general, or usually, omega cutoff is equal to omega s over 2. And therefore, we can write this as x continuous of nt multiplied by sine omega s over 2 multiplied by t minus nt divided by omega s over 2 multiplied by t minus n multiplied by t.
Why does it replace pi?
What is it?
Why does the WS replace pi?
What happened to the t?
There is the t here. We're going to bring it over pi over t.
Oh, okay.
Make sense? This is the same as writing pi over t, which is omega s over 2. Okay. So again, by default, the cutoff of the filter is going to equal to omega s over 2. Makes sense? If I'm sampling at a certain rate, I'm going to design my filter to be at omega s over 2. Okay, now the question I'm going to ask you, and then we'll share a graph. Is h of j omega realizable? Yes or no?
The ideal filter?
Yeah, this ideal filter, is it realizable?
No.
No. Why is it not?
Because that cutoff is too steep, or be, oh, I don't remember the term, but it'd be a bit more of a slope.
Quality factor, right?
What else? I mean, what bothers us the most about h of the filter, this sink? We have the interpretation filter. This filter looks something like this. Why is it not realizable, this filter? Because, I mean, apparently, it goes from negative infinity to infinity. It is not causal. I mean, you see it. Why is it not causal? Is it causal? This is h of t. It is not causal. Anybody knows why?
What's causal mean again?
The output cannot happen before the input. This is the impulse response. The impulses are right here. There's already an output here. So this is not causal. Okay. So no, and y, first, h of t is non-causal. Second, the equation above requires infinite number of samples. I have the summation from negative infinity to infinity of x. I have infinite number of samples. And third, the equation requires infinite number of additions and multiplications. Can you read this as multiplications? Okay. So apparently this is an ideal filter that is physically not realizable. Now let's see how this looks like. How does this reconstruction look like? So let's say that I have samples that look something like this. This is t, this is 0, t, 2t, 3t, etc. What's going to happen when I apply this to this filter h of t? Each one of these is going to generate a sink. Agree? So therefore, I'm going to get a sink that's going to look something like this from this impulse here. The second one is going to also generate a sink for me. The third one is going to generate a sink for me. Together? When I add all these together, how does the signal going to look like? It's going to look something like this. I'm not going to see all these added. I'm not going to see all these things. I'm going to see the addition of all of them. I'm going to see a continuous signal that looks like this. Does that make sense? Everybody? How it works? Now, if I do this in MATLAB, here is another example. I have a signal, I have a pulse that I sample, and I'm trying to reconstruct. I did the same thing. I took samples, I sample, I pass them through the filter. What does the filter do? There's a sink each time an impulse goes through. When I add them together, how does it look like? It looks like this. Make sense? Why does it not look like an ideal pulse? You know what I'm asking?
You don't have samples in between those.
No, what
If you
else?
had more samples, it would look better.
Well, more samples. Excellent. So what I'm saying,
It's not ideal because the way it was made isn't ideal.
because I did not, if for it to be ideal, I have to take all these, I mean, this is realizable or semi-realizable. If I want it to be ideal, I have to take infinite number of samples, I have to take infinite number of summations, I have to take the sink from negative infinity to infinity and add them together. Make sense? Instead, what I've done is I took a finite length of that sink. So ideally, this should be like this.
So between the two samples, is that interpolated? Is that what that is?
No, between these samples here, this is just the addition of these.
Okay,
Does that make sense?
sure.
Here is going to be exactly the value of the sample. Here is going to be exactly the value of the sample. Between them, this sink, all the million sinks going to add up together to whatever this value is. Make sense? However, when I've done it here, I took a finite length sink. So instead of the sink, ideally the sink should go from negative infinity to infinity. I took the sink to be finite. I came after a stage and I said, okay, this is very small. I'm going to take a finite length of the sink that I've used in here. So the sink that I use has a finite length. Together? But if I were to add an infinite number, if I were to allow the sink to go from negative infinity to infinity, then this will add up, ideally, to that pulse that is going to look like an ideal pulse. Does that make sense, everybody? Is that clear? So this is the magic of this filter. So hopefully now everybody, when we say a low-pass filter, what is a low-pass filter? In the frequency, it's direct, that's going to cut everything, but we should be able to also understand in time domain. The time domain is the sink. And that sink is going to convolve these impulses such that when I connect them, it's going to give me a low frequency signal. That is the original signal that I sampled. Is that clear, everybody? So this is, let's say this is my original signal. I sampled this original signal. I took these samples here, this sample, this sample, this sample, etc. And now I reconstructed the original signal. Okay. We have 2 minutes, so we'll look at some practical consideration. What are the practical considerations when we consider the sampling? The first consideration is that we assume the signal that we're sampling is band limited. However, in practice, the input signal is not going to be band limited to a frequency FM hertz. Why is it not going to be band limited to a frequency FM?
Noise?
Because if the signal is time limited, it's going to be frequency unlimited. Make sense? If the signal in the time domain is limited, it only exists over a finite amount of time, then the frequency is going to be unlimited. And practically, most of the signal are not going to be band limited. So what do we do to solve this problem? So what do we do if I have to sample a signal? I came to this signal that I want to sample, and I look at the spectrum, and the spectrum looks something like this.
We ignore some of it?
What is it?
We ignore some of
Excellent. We can say, okay, this is going from negative infinity. I cannot sample it. What do I have to do? I'm going to say, okay, where are the major components of this signal? I'm going to keep them, and then I'm going to remove the rest of it. So what we're going to do, and we'll see this in the next class, I'm going to come here. I'm going to pass the signal before I sample it to a filter that is going to remove all these high frequency components. Make sense? Any questions? Okay, we'll stop here.